Oh, sorry. Didn't see you there. This camera's too high. What's going on, guys? What's up? I'll leave the window open. I'm gonna leave the window open. I'm gonna leave the window open. I'm gonna leave the window open. Guys, so what have I been doing today? Well, I made some bread by tutoring. What else? What else? What else? What else? I also one of the challenges, okay, for the 1A one day podcast, shout out, go to at official 1A productions on YouTube. Okay, go there, right? What am I gonna, what are the, hold up, what are the tags? Hold on, guys, I gotta set the tags. Don't you remember tags? Premium life, winning, motivation, self help, grind set, cool, work, epic, win. That's what's popping to the mind. But I had to work on this track, okay, which I'll play. I'll give a sneak preview for the live people. All right, this is a song right here, song of the century if you ask me. But if you ask me,
This beat gave me cerebral palsy.
try to do a little ad lib there. That's me on the mic. That's me on the mic. And then the song part. And then watch this up. Watch this. Watch this.
Fuck that singing, I'm about to rapping. No idea what's gonna happen. Maybe Drake will give me a call, but I don't want his 30 foot long. I'm a sandwich man, making a plan. All the things that I said I would do, damn. Baby, 100% I'm the man. Now fuck this beat, I'm switch up the jam.
Oh shit! A beat switch? No way!
You won't fuck with me.
Get aggressive.
You won't fuck with me. Hey, you won't fuck with me. Hey, switch up like I'm a dog. Hey, bitch, I'm a dog. Bitch, I'm a dog. Now you fucked up, bitch.
Okay, so the whole point of that song, right? It's to basically it's to try make a song in like a style or a genre that I've never done before, or that I don't do really commonly at all. So one of them, hip hop, first thing that came to my mind. I don't rap. Second, a little bit more of like a glitch sample based. I haven't done sample based music in a long time. But also I don't really do like glitchy stuff kind of thing. And I've also I don't think I've ever done a beat switch in one of my songs in the middle of the song. I don't think I've ever done one of those. So it's fun. It's fun to do. But guys, you know, a part of the premium life, okay? Something that's a part of the premium life. Should I turn off the... I just look weird. I look sickly and unhealthy. Maybe it's because I haven't been getting in my 10K steps. Maybe that's why. How many steps have I had today? Let's check. 2.4K steps. That's about it. You know what those 2,000 steps were for? Those steps were to go to Chipotle and get a chicken burrito. That's right. Oh. Okay. Okay. So you know the premium life, it's not just all about fun and games, okay? We don't get live on premium life to play games. Okay. The game streams are for gaming. It's separate from the premium. Actually no, premium life includes and ultimately premium life would include a balance of all things, right? But on premium on this on this episode of Premium Life, we're not playing games. Okay, we got on live in order to guess what it is. Oh, I bet you don't know what it is. Bet you don't know what it is. I'm still setting it up. Oh my god. That's right, guys. On this special 420 Blaze It episode of Premium Life. Episode 2, Day 2, Episode 2. On this special episode of Premium Life, okay? Actually, wait. When was the last time I streamed this? I'm fucking tired, dude. Why was my original thumbnail so much... Why was it so much brighter? Is it because I had the monitor brighter? It's because I had the monitor brighter. Yeah, do I want this monitor to burn into my eyes? Maybe. Maybe not. Okay. I think my biceps are finally recovering. Oh, I should see.
Hey, Miss Donda, you run and tell my mama, please tell her I say something. Believe ain't no such thing as no after over, this is it done. If there's a heaven, you would think they let you speak to your son. Maybe she has in the form of a baby's laugh. I heard passing by in a stroller, reminded me, hey, keep rolling on, no. Maybe she has with the prick of a blade of grass. I've been laying on way too long.
One thing that a lot of people don't know is you can actually just plug your film in once you've exposed it to USB-C. It shows up here on your computer. You can also plug into the 120 format rules here as well. So if you're shooting media format, just plug right in, it goes right to your computer. One thing that a lot of people don't know is you can actually just plug your film in once you've.
Let's see. What do we want to play today? Alpine Inn. What's this one? Oh. Hells yeah. Girl, you know it's true. Ooh, ooh, ooh. I love you, ooh.
First month I won't be able to afford rent. I'm not a rich person. I don't have a lot of
This old school Italian deli is serving up some of the best sandwiches in San Francisco. They're also one of the oldest delis in the country. We're at Molinari Delicatessen in North Beach, which has been owned and operated by 4 generations of the same family since 1896. They make their own salami, sausages, and this old school Italian deli is serving up some of sauces and fresh pastas. Their most popular sandwich orders include the Molinari Special Italian Combo, Luciano Special, and the Renzo. It's almost an SF local rite of passage to eat here. Grab a made-to-order sandwich for lunch and enjoy it at one of their outdoor tables or over at Washington Square Park.
This is what life is all about.
Yeah, guys. Okay, leave me alone. Can a guy not go on his phone for a little bit? Go on your phone. The whole world goes wild. What's the meme? Go on your phone. No one bats an eye. Something, something. The whole world cries. I don't know. Oh, dude. I recorded and edited one YouTube vid already. Should I record another YouTube video? I could record a video on not multitasking. I could do that. What time is it? It's about... It's almost going to be the time. When the sun starts shining over there, I might record it. Okay, insulators. God damn it. Why is it that clicking on this brings me back to this? Why is that the case? I don't know. It's kind of a stupid design. In Chapter 11, when we discussed the tight binding model in one dimension, we introduced some of the basic ideas of band structure. In Chapter 15, we found that an electron in a periodic potential shows exactly the same type of band structure as we found for the tight binding model. Did we do that? I guess so. In both cases, we found that the spectrum is periodic in momentum. So all momenta can be taken to be in the first Brion zone in reduced zone scheme, and that gaps open at Brion zone boundaries. These principles, the idea of bands and band structure, form the fundamental underpinning of our understanding of electrons and solids. In this chapter, and the next, we explored these ideas in further depth. Depth? Really? Energy bands in one dimension. As we pointed out in Chapter 13, the number of K-states in a single Brion zone is equal to the number of unit cells in the entire system. I guess so. The number of K-states is equal to the number of unit cells. Yeah. Thus, if each unit cell has exactly one free electron, i.e. valence 1, There would be exactly enough electrons to fill the band if there were only one spin state of the electron. Yeah. Being that there are two spin states of the electron, when each unit cell has only one valence electron, then the band is precisely half full. This is shown in the left of figure 16.1. Here, there is a Fermi surface where the unfilled states meet the filled states. In the figure, the Fermi energy is shown as a horizontal dashed line. When a band is partially filled, the electrons can repopulate when a small electric field is applied, allowing current to flow as shown in the right. What? I was thinking about something else. This is shown in the left, blah, blah, blah. Here, the Fermi surface, there's a Fermi surface where the unfilled states meet the filled states. In the figure, the Fermi energy is shown as a horizontal dashed line. Okay. When a band is partially filled, the electrons can repopulate when a small electric field is applied, allowing current to flow, as shown in the right. Thus, the partially filled band is a metal. Okay. On the other hand, if there are 2 electrons per unit cell, then we have precisely enough electrons to fill one band. One possibility is shown on the left of figure 16.2. The entire lower band is filled and the upper band is empty, and there's a band gap between the 2 bands. Note that the chemical potential is between the bands. When this is the situation, the lower band is known as a valence band, and the upper band is known as the conduction band. Valence band, conduction band. In this situation, the minimum energy excitation is created by moving an electron from the valence to the conduction band, which is non-zero energy. Because of this, at 0 temperature, a sufficiently small electric perturbation will not create any excitations. The system does not respond at all to electric. The system does not respond at all to electric fields. Thus, systems of this type are known as electrical insulators, or more specifically, band insulators. So what was the argument with the 0 temperature? What is this? In this situation, the minimum energy excitation is created by moving an electron from the valence to the conduction band, which is non-zero energy. Because of this, at 0 temperature, a sufficiently small electric perturbation will not create any excitations. Yeah, the system doesn't respond at all to electric field. Thus, systems of this type are known as electrical insulators, or more specifically, band insulators. If the band gap is below about 4 electron volts, then these type of insulators are called semiconductors. Since at room temperature, a few electrons can be thermally excited into the conduction band, and these electrons then can move around freely, carrying some amount of current. One might want to be aware that in the language of chemists, a band insulator is a situation where all of the electrons are tied up in bonds. For example, in diamond, carbon has valence 4, meaning there are 4 electrons per atom in the outermost shell. In the diamond crystal, each carbon atom is covalently bonded to each of its 4 nearest neighbors, and each covalent bond requires 2 electrons. 1 electron is donated to each bond from each of the 2 atoms on either end of the bond. This completely accounts for all of the 4 electrons in each atom. Thus, all of the electrons are tied up in bonds. This turns out to be equivalent to the statement that certain bonding bands are completely filled, and there is no mobility of electrons since there are no partially filled bands. Boom. Oh boy. This is great. Excuse me, did you just slam your phone? Yes, I did. What are you gonna do about it? What is this? When there are 2 electrons per atom, one frequently obtains a band insulator as shown in the left of figure 16.2. However, another possibility is that the band energies overlap as shown in the right of figure 16.2. In this case, although one has precisely the right number of electrons to fill a single band, instead one has 2 partially filled bands. As in 16.1, there are low energy excitations available and the system is metallic. Why would this happen though? Oh, let's ask ChatGPT. Why would Okay, it didn't explain anything. That's okay, I guess I just don't need to know it. This looks fucking weird. Fermi surfaces. Potassium is like an egg. Boy, people who do this for a living. This is funny. I don't know why, it's just like funny shapes. Okay, there's not that much pages to this. Oh, I'm so tired, guys. I've never been more awake in my life. Okay. Oh, I know what. I know what we're missing. Guys, you didn't even tell me. You didn't even tell me. Why didn't you even tell me that we were missing the 3DS first time setup lost music? Come on, guys. It is useful to try to understand how the nearly 3-electron model results in band structure in 2 dimensions. Let us consider a square lattice of monovalent atoms. The Brillouin zone is correspondingly square, and since there is 1 electron per atom, there should be enough electrons to half fill a single Brillouin zone. In the absence of a periodic potential, the Fermi sea forms a circular disk as shown in the left of figure 16.3. I'm not even reading right now, I'm just thinking. Left. In the absence of a periodic potential, the Fermi sea forms a circle whose area is precisely half that of the Brion zone. Middle. When a periodic potential is added, the states closer to the zone boundary are pushed down in energy, deforming the Fermi sea. Right. With strong periodic potential, the Fermi surface touches the Brion zone boundary. The Fermi surface remains continuous since the Brion zone is periodic. Okay. In the absence of a periodic potential, the Fermi sea forms a circular disk as shown in the left of figure 16.3. The area of this disk is precisely half the area of the zone. Now, when a periodic potential is added, gaps open up at the zone boundaries. This means that states close to the zone boundary. This means that states close to the zone boundary get moved down in energy, and the closer they are to the boundary, the more they get moved down. I'm not understanding what's happening right now. Like, I'm not getting it. I don't get it. I don't get it. I don't get it. I don't get it, Mr. Krabs. I'm not getting it. Okay, I am so not focused. Guys, okay. This is premium life, guys. To focus, we have to change our posture a little bit, right? Okay. And we have to eliminate distractions, so that means phone will be face down out of my view. It's going to be in the corner. Okay. Okay. It is useful to try to understand how the nearly free electron model results in band structure in 2 dimensions. Let us consider a square lattice of monovalent atoms. So a square lattice of monovalent atoms. Yeah, okay. The Brion zone is correspondingly square, and since there is 1 electron per atom, there should be enough electrons to fill half fill a single Brion zone. Yeah, okay. So there's a lattice, square lattice, right? And there's enough electrons to fill exactly half of this. So the electrons will kind of, like what? Fucking... I guess this would be half? I don't know. Something like this. Half. The Fermi sea forms a circular disk, yeah. The area of this disk is precisely half the area of the zone. Now, when a periodic potential is added, gaps open up at the zone boundaries. This means that states close to the zone boundary get moved down in energy, and the closer they are to the boundary, the more they get moved down. The states close to the boundary get filled up preferentially at the expense of states further from the boundary. This deforms the Fermi surface, roughly as shown in the middle. So it's saying that our circle is then, so points that are closer to the zone boundary. What is it saying? Gaps open up at the zone boundaries. This means that the states close to the zone boundary get moved down in energy. They get moved down in energy? What does this mean? As a result, states close to the boundary get filled up preferentially at the expense of states further from the boundary. Ah. Okay, gaps open up at the zone boundaries. This means that states close to the zone boundary. Oh, gaps get opened up. So then states close to the zone boundary move down in energy. So thus, the ones at the zone boundary will be filled up a little bit more. So it'll do something like that, I guess. According to this. If the periodic potential is strong enough, the Fermi surface may even touch the Brion zone boundary, as shown in the figure on the right of 16.3. Although this looks a bit strange, the Fermi space remains perfectly continuous since the Brion zone is periodic in K space. Thus, if you walk off the right-hand side, you come back in the left. If you walk off, you come back. It's like Pac-Man. Waka, 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 waka. The physics shown in 16.3 is quite similar to what is seen in many real materials. In figure 16.4, we show that the Fermi surfaces for the monovalent metals potassium, lithium, and copper. Potassium is an almost ideal free electron metal with an almost perfectly spherical Fermi surface. For lithium, the Fermi surface is slightly distorted, bulging out near the zone boundaries. For copper, the Fermi surface is greatly distorted, touching the Brion zone boundary in tubes. In all three cases, however, the Fermi seas fill exactly half the Brion zone volume, since the metals are monovalent. Okay. It's hard to tell, but sure. What is this? Okay. Oh, the sunlight's coming in. Should I record that video? No, I'm too tired. Recording that video is not going to be... It's not going to be a good video. When did I record that video? What the hell? April 14th. When was April 14th? I was on Sunday. Okay. I'm really tired. I think the premium life solution for this is to take a 10-minute nap. So guys, I will take a 10-minute nap. I swear it'll be 10 minutes. Set a timer for 15 minutes. I say 15 minutes because it's going to take me, you know, a couple minutes to actually lay down. But yeah, I'll be back in 10 minutes. 15 minutes after a 10-minute nap. Well, folks, what did I say? What did I say? I said a 10-minute nap. I said I'll be back in 15 minutes about. And it's been about 15 minutes. So, guys, what I'm going to do is I'm going to finish reading this chapter. Easy, easy, easy. And then I'm going to go for a walk. Holy fuck, chapter 17 is long as fuck, dude. What about chapter 18? How long is chapter 18? Okay, I guess I have to read the rest of this tomorrow. But anyways, yeah. So let's keep reading, guys. Let's keep reading. Let us now consider the case of a two-dimensional square lattice of divalent atoms. In this case, the number of electrons is precisely enough to fill a single zone. In the absence of a periodic... I'm reading, but I'm not absorbing. Let us now consider the case of a two-dimensional square lattice of divalent atoms. Divalent. In this case, the number of electrons is precisely enough to fill a single zone because it's divalent. In the absence of a periodic potential, the Fermi surface is still circular, although it now crosses into the second Brion zone, as shown on the left of figure 16.5. Again, when a periodic potential is added, a gap opens at the zone boundary. This gap opening pushes down the energy of all states within the first zone, and pushes up the energy of the states in the second zone. If the periodic potential is sufficiently strong, then the states in the first zone are all lower in energy than states in the second zone. As a result, the Fermi sea would look like the right of figure 16.5. Since there is a gap at the zone boundary, there are no low energy excitations possible, and the system is an insulator. It is worth considering what happens for intermediate strength of the periodic potential. Again, states outside of the first Brion zone are raised in energy, and states inside the first Brion zone are lowered in energy. States outside are raised, and states inside are lowered. Therefore, fewer states will be occupied in the second zone and more states occupied in the first zone. However, for intermediate strength of potential, some states will remain occupied in the second zone and some states will remain empty within the first zone, as shown in figure 16.6. In a reduced zone scheme, we would say that there are some states filled in the second band and some empty in the first band. This is precisely analogous to what happens in the right half of figure 16.2. Oh. That's what's happening. Is this going to be a hole? For intermediate strength of potential, some states will remain occupied in the second zone and some states will remain empty within the first zone. Some states are occupied in the second zone, some states remain empty in the first zone. This is precisely analogous to what happens in the right half. There will still be some low energy excitations available and the system remains a metal. This physics is quite common in real materials. In figure 16.7, the Fermi surface of the divalent metal calcium is shown. As shown in the cartoon, the Fermi surface intersects the Brion zone boundary, and although there are precisely enough electrons to completely fill the first band, instead the lowest two bands are each partially filled, and thus calcium is a metal. We emphasize that in the case Yeah, the Fermi surface. Yeah. So the Fermi surface is a divalent. Wait, where's calcium? What the fuck? We emphasize that in the case where there are many atoms per unit cell, we should count the total valence of all of the atoms in the unit cell put together to determine if it is possible. What the fuck did I just read? We emphasize that in the case where there are many atoms per unit cell, we should count the total valence of all the atoms in the unit cell put together to determine if it is possible to obtain a filled band insulator. If the total valence of all the atoms in the unit cell is even, then for strong enough periodic potential, it is possible that some set of low energy bands will be completely filled. There will be a gap, and the remaining bands will be empty, i.e. it will be a band insulator. However, if the periodic potential is not sufficiently strong, bands will overlap and the system will be a metal. Okay. I'm not quite fully getting like the intuition behind why like a periodic potential causes some like unfilled gaps. Yeah, you can estimate how strong the potential needs to be. We need to have the highest energy state in the first Brion zone. State in the first Brion zone be lower energy than the lowest energy state in the second energy zone. The high energy state in the first zone in the absence of periodic potential is a zone corner and therefore has an energy E corner. 2 h bar squared pi over 2 squared over 2 ma squared. The lowest energy state in the second zone is in the middle of the zone boundary. This is going to be h bar squared pi over 2 squared over 2 ma squared. Thus we need to open up a gap at the zone boundary which is sufficiently large. Okay. So far in this chapter, we've described band structure in terms of the nearly free electron model. Similar results can be obtained starting from the opposite limit, the tight binding model introduced in chapter 11. In this model, we imagine some number of orbitals on each atom and allow them to only weakly hop between orbitals. This spreads the eigenenergies of the atomic orbitals out into bands. Writing down a 2 or 3-dimensional generalization of the tight binding Hamiltonian is quite straightforward and is a good exercise to try. One only needs to allow each orbital to hop to neighbors in all available directions. The eigenvalue problem can then always be solved with a plane wave ansatz analogous to equation 11.5. The solution of a tight binding model of atoms, each having a single atomic orbital on a square lattice, is given by... Dude, I'm not absorbing like any of this. What the fuck? It's like, this is a very picturesque kind of thing, and they don't have many pictures. They have pictures, but not many. Equaenergy contours for this expression are shown in figure 16.8. Note the similarity in the dispersion to our qualitative expectations shown in figure 16.3 and figure 16.6, which were based on a nearly free electron picture. In the above described tight binding picture, there is only a single band. However, one can make the situation more realistic by starting with several atomic orbitals per unit cell to obtain several bands. Another good exercise to try. As mentioned in section 6.2.2 and chapter 11, as more and more orbitals are added to a tight binding calculation, the results become increasingly accurate. In the case where a unit cell is divalent, it is crucial to determine whether bands overlap. This, of course, requires detailed knowledge of the band structure. In the tight binding picture, if the atomic orbitals start sufficiently far apart in energy, then small hopping between atoms cannot spread the bands enough to make them overlap. In the nearly free electron picture, the gap between bands formed at the Brion zone boundary is proportional to Vg, and it is the limit of strong periodic potential that will guarantee that the bands do not overlap. Qualitatively, these two are the same limit, very far from the idea of a freely propagating wave. Okay. Okay. Come on. Come on. Oh. Guys, the premium life didn't account for being tired. How do you stop being tired? You do drugs. Caffeine. Okay. Failures of the band structure picture of metals and insulators. The picture we have developed is that the band structure and the filling of bands determines whether a material is a metal or insulator, or semiconductor, meaning an insulator with a small band cap. One thing we might conclude at this point is that any system where the unit cell has a single valence electron must be a metal. However, it turns out this is not always true. The problem is that we have left out a very important effect, Coulomb interaction between electrons. We have so far completely ignored the Coulomb repulsion between electrons. Is this neglect justified at all? If we try to estimate how strong the Coulomb interaction is between electrons, roughly E squared over 4 pi epsilon naught r, where r is the typical distance between two electrons, i.e. the lattice constant A, we find numbers on the order of several electron volts. This number can be larger or even far larger than the Fermi energy, which is already a very large number on the order of 10,000 Kelvin. Given this, it is hard to explain why it is at all justified to have thrown out such an important contribution. In fact, one might expect that neglecting this term would give complete nonsense. Fortunately, it turns out that in many cases it is justified to assume non-interacting electrons. The reason this works is actually quite subtle and was not understood until the 1950s due to the work of Lev Landau. This rather deep explanation, however, is beyond the scope of this book, so we will not discuss it. Nonetheless, with this in mind, it is perhaps not too surprising that there are cases where the non-interacting electron picture, and hence our view of band structure, fails. A case for the magnets. A case where the band picture of electrons fails is when the system is ferromagnetic. We will discuss ferromagnetism in details in chapter 20 and 23, but in short, this is where, due to interaction effects, the electron spins spontaneously align. From a kinetic energy point of view, this seems unfavorable since filling the lowest energy eigenstates with both spin states can lower the Fermi energy compared to filling more states with only a single spin type. However, it turns out that aligning all of the spins can lower the Coulomb energy between the electrons, and thus our rules of non-interacting electron band theory no longer hold. Mott insulators. Another case where interaction physics is important is the so-called Mott insulator. Consider a monovalent material. From band theory, one might expect a half-filled lowest band, therefore a metal. But if one considers the limit where the electron-electron interaction is extremely strong, this is not what you get. Instead, since the electron-electron interaction is very strong, there's a huge penalty for two electrons to be on the same atom, even with opposite spins. Okay, what? Consider a monovalent material. From band theory, one might expect a half-filled lowest band, therefore a metal, but if one considers the limit where the electron-electron interaction is extremely strong, this is not what you get. Instead, since the electron-electron interaction is very strong, there is a huge penalty for two electrons to be on the same atom, even with opposite spins. As a result, the ground state is just one electron sitting on each atom. Since each atom has exactly one electron, no electron can move from its atom, since that would result in a double occupancy of the atom it lands on. As a result, this type of ground state is insulating. Arguably, this type of insulator, which can be thought of as a more or less of a traffic jam of electrons, is actually simpler to visualize than a band insulator. We will also discuss Mott insulators further in section 19.4 and particularly 23.2. Band structure and optical properties. To the extent that electronic band structure is a good description of the properties of materials, and usually it is, one can attribute many of the optical properties of materials to this band structure. Optical properties of insulators and semiconductors. Band insulators cannot absorb Band insulators cannot absorb photons, which have energies less than their band gap energy. Yeah, because photons have energy less than their band gap energy. The reason for this is that a single such photon does not have the energy to excite an electron from the valence band into the conduction band. Since the valence band is completely filled, the minimum energy excitation is of the band gap energy, so a low energy photon creates no excitations at all. As a result, these low energy photons do not get absorbed by this material at all, and they simply pass right through the material. Oh, what? Okay. Light absorption spectra are shown for 3 common semiconductors in figure 16.9. Silicon, gallium arsenic? Fuck. And germanium. Note for the example the strong drop in the absorption for gallium arsenic, I don't know, for wavelengths greater than about 0.86 micron corresponding to photon energy is less than the band gap energy of 1.4 for electron volts. Let us now recall the properties of visible light shown in table 16.1. With this table in mind, we see that if an insulator or wide bandgap semiconductor has a bandgap greater than 3.2 electron volts, then it appears completely transparent since it cannot absorb any wavelength of visible light. Materials such as quartz, diamond, aluminum oxide, and so forth are insulators of this type. Semiconductors with somewhat smaller band gaps will absorb photons with energies above the band gap, exciting electrons from the valence to the conduction band, but will be transparent to photons below this band gap. So semiconductors with somewhat smaller band gaps will absorb photons with energies above the band gap, but will be transparent to photons below this band gap. For example, cadmium sulfide is a semiconductor with a band gap of roughly 2.6 electron volts, so that violet and blue light are absorbed, but red and green light are transmitted. As a result, this material looks reddish. Semiconductors with very small band gaps, such as that, look black since they absorb all frequencies of visible light. Fuck, I just realized my argument on homework about the wavelength being smaller than the band gap is not exactly correct. It's not the wavelength, it's the energy. Because band gaps deal with K-space. Okay. Direct and indirect transitions. While the band gap determines the minimum energy excitation that can be made in an insulator or semiconductor, this is not the complete story in determining whether or not a photon can be absorbed by a material. It turns out to matter quite a bit at which values of K the maximum of the valence band and the minimum of the conduction band lies. If the value of K for the valence band maximum is the same as the value of K for the conduction band minimum, then we say that it is a direct band gap. If the values of K differ, then we say that it is an indirect band gap. So if the value of K for the valence band maximum is the same as the value of K for the conduction band minimum, for the valence band maximum and the conduction band minimum, then we say that it is a direct band gap. If the values of K differ, then we say it is an indirect band gap. For example, the system shown on the left in 16.2 is a direct band gap, because the valence band maximum and conduction band minimum. But if they're off, then it's indirect, where both the valence band maximum and the conduction band minimum are at the zone boundary. In comparison, if the band shapes were as in the right of figure 16.2, but the band gap were large enough such that it would be an insulator, this would be an indirect band gap since the valence band maximum is at the zone boundary, but the conduction band minimum is at k equals 0. One can also have both indirect and direct band gaps in the same material, as shown in figure 16.10. So what was 16.9? What? Oh, 16.2. Why would I scroll back to fucking 16.2? Yeah, this is also indirect, yeah, because it's both, like, bottom things, yeah. No, what am I talking about? In this figure, the minimum energy excitation is the indirect transition, meaning excitation of electron across an indirect band gap, or equivalently a transition of non-zero crystal momentum, where the electron is excited from the top of the valence band to the bottom of the conduction band at a very different K. While this may be the lowest energy excitation that can occur, it is very hard for this type of excitation to result from exposure of the system to light. The reason for this is energy momentum conservation. If a photon is absorbed, the system absorbs both the energy and the momentum of the photon. But given an energy E in the electron volt range, the momentum of the photon h bar k equals E over c is extremely small because c is so large. Thus, the system cannot conserve momentum while exciting an electron across an indirect band gap. Nonetheless, typically if a system like this is exposed to photons with greater energy than the indirect band gap, a small number of electrons will manage to get excited, usually by some complicated process including absorption of a photon, exciting an electron with simultaneous emission of a photon to arrange the conservation of energy and momentum. What the fuck? Nonetheless, typically, if a system like this is exposed to photons with energy greater than the indirect band gap, a small number of electrons will manage to get excited, usually by some complicated process including absorption of a photon, exciting an electron with simultaneous emission of a phonon to arrange the conservation of energy and momentum. In comparison, if a system has a direct band gap and is exposed to photons of energy greater than this direct band gap, then it strongly absorbs these photons while exciting electrons from the valence band to the conduction band. If a system has a direct band gap, then it strongly absorbs these photons while exciting electrons from the valence band to the conduction band. In figure 16.9, the spectrum of GE shows weak optical absorption for energies lower than its direct band gap of 0.8 electron volts. This is due to excitations across its lower energy indirect band gap. Okay. The optical properties of metals are a bit more complicated than that of insulators. Since metals are very conductive, photons, which are electromagnetic, excite the electrons, which then re-emit light. This re-emission or reflection of light is why metals look shiny. Noble metals, gold, silver, platinum, look particularly shiny because their surfaces do not form insulating oxides when exposed to air, which many metals, such as sodium, do within seconds. Ah. Oh, so they're very conductive. So photons excite the electrons which re-emit the light. So this re-emission of light, or reflection, is why they look shiny, because they're super conductive. Oh. Even amongst metals, ignoring possible oxide surfaces, colors vary. For example, silver looks brighter than gold and copper, which look yellow or orangish. This again is a result of the band structure of these materials. All of the noble metals have valence 1, meaning that a band should be half filled. However, the total energy width of a conduction band is greater for silver than it is for gold or copper. In tight binding language, T is larger for silver. This means that higher energy electronic transitions within the band are much more possible for silver than they are for gold and copper. For copper and gold, photons with blue and violet colors are not well absorbed and re-emitted, leaving these materials looking a bit more yellow and orange. For silver, on the other hand, all visible colors are re-emitted well, resulting in a more perfect or white mirror. For copper and gold, photons with blue and violet colors are not well absorbed and re-emitted, leaving the material... okay. While this discussion of the optical properties of metals is highly oversimplified, really there are many bands overlapping in these materials, and the full story addresses inter and intra-band transitions. It captures the correct essence, that the details of the band structure determine which color photons are easily absorbed and or reflected, and this in turn determines the apparent color of the material. Optical effects of impurities. It turns out that small levels of impurities put into periodic crystals, particularly into semiconductors and insulators, can have dramatic effects on many of their optical as well as electrical properties. For example, 1 nitrogen impurity per million carbon atoms in a diamond crystal gives a crystal a yellowish color. 1 boron atom per million carbon atoms gives the diamond a bluish color. We will discuss the physics that causes this in section 17.2.1. Chapter summary. Here we are, guys. A material is a metal if it has low energy excitations. This happens when at least one band is partially filled. Band insulators and semiconductors have only filled bands, and empty bands have only filled bands and empty bands and have a gap. Insulators and semiconductors have only filled bands and empty bands and have a gap for excitations. This is written so poorly. It's written so poorly. A semiconductor is a band insulator with a small band gap. The valence of a material determines the number of carriers being put into the band, and hence can determine if one has a metal or insulator/semiconductor. However, if bands overlap, one might not be able to fill the bands to a point where there is a gap. The gap between bands is determined by the strength of the periodic potential. If the periodic potential is strong enough, bands will not overlap. The band picture of materials fails to account for electron-electron interaction. It cannot describe interaction-driven physics such as magnetism and Mott insulators. Optical properties of solids depend crucially on the possible energies of electronic transitions. Photons can easily create transitions within low momentum, but cannot create transitions with larger momentum easily. Optical excitations over an indirect gap are therefore weak. I like these chapter summaries, but I feel like they should be placed at the end of every section. I feel like there should be a section summary. I feel like that would be most effective for learning. But anyways. Okay, that's it for Premium Life, day 2. Okay, we read through one chapter, but we're really tired, which is something that the Premium Life did not consider. We did not get a good night's rest of sleep, and also we ate Chipotle, which has a lot of carbs, so that's probably making us tired as well. So, peace out.